In this video, I'll briefly talk about the collision theory and factors that affect the rate of the reactions. I'm going to go ahead and start with the collision theory first. And for any reactions to take place, the very first thing you must have the reactants should be colliding with one another. So let me just go ahead and take an example, and that is going to be the very first condition for the collision theory, that you must have the molecules colliding with one another. And on the top of that, you must have a proper orientation when they are colliding. Now, what does that really mean? So let me take an example of, suppose I got an AB kind of going on to make an A2 and a B2. So to balance this, I'm going to go and write down 2AB in the front. So I have this reaction here where the reactant AB is going to be getting broken down to make A2 and B2. So if I'm looking at what bonds are being broken here, I can talk about the bond AB must be broken up. So this bond must be broken, and then when I'm looking on the product side, I must have an AA bond being made and a BB bond being made. Now, whether it's in a single bond, double bond, that's in a different story with just in a generic reaction. Now I got this bond between A and B that needs to be broken up, and then the bond between AA and a BB must be made. Now I know I have two molecules of AB for in a balanced equation, so those two molecules of AB must be colliding with one another. That's one condition, and they must show, or they must collide with the proper orientation. So if I look at an example where, suppose I have an AB colliding with another AB molecule that looks something like this. So I'm looking at here that the collision being taken place where the B of first molecule is kind of colliding with the A of the second molecule. Now that's not really a good collision. That's a bad collision, even though the collision is happening, but it does not have a proper orientation, because what we're really looking at is that A must be making another bond with A. So I want to have A colliding with A, not A colliding with B. So let me write up another orientation where maybe possibly I have an AB here, and then I have another molecule of AB right below it, and this is how they're kind of colliding in this particular case. And it seems like this is in a better orientation collision here. So along with having the molecules colliding with one another, you must also have a proper orientation. Now, if you have a collision that does not have a proper orientation, they would not make any products. So no products would be made here. Now, when you have a collision with a good orientation, it may make product. Now, that does not mean it's always going to make the product, but it will have at least first condition kind of cleared up here, that you have at least in a good collision here where they may make the product. Now, how do I know whether or not this will actually make product? Now, once you have a collision within a proper orientation, the second condition with the collision theory is you must have enough energy to overcome the energy of activation. Like for example, if I'm looking at a energy profile diagram where, suppose this is where the A B molecule here is, and then I'm going to be making an A2 and B2 as my product. Now your reaction profiles, typically it has to break in an AB bond, so it requires some energy in the beginning, so it's probably going to go a little bit uphill before it comes back down. So you can see here that my activation energy for this particular case is going to be this much here. So now the collision between an AB molecule, after making sure that it's got a proper orientation, those particular collisions must have enough energy so that they can overcome this activation energy, which actually going to be needing to break the old bonds, and then eventually you're going to be making new bonds, and that's when you actually release energy. So if you don't have enough energy to overcome the energy of activations, even the good orientation collisions will not make product. So those are the two main criteria that you really got. First, you must have collisions with proper orientation, and then the second, the collision with proper orientations must have enough energy to overcome the energy of activation. Now, you don't really have a lot of control on those things. Like, for example, how can I make sure that when these molecules are colliding with one another, they should collide with an proper orientation? And the answer, simple answer, you don't have any control on them. But what you could possibly do to make sure that you would have more collisions with proper orientation, well, you can just increase the frequency of the collisions to begin with. Like, let's suppose I have 10 collisions in 1 second for a minute, for a second here. So in those 10 collisions, maybe I have 8 of them being bad collisions, a bad orientation, and only 2 of them are good orientation. But then if I could somehow increase those 10 collisions per second to maybe 20 collisions per second, then I would ramping up the amount of bad collisions, but I'm also ramping up the amount of good collisions or good orientation collisions, and that would eventually make the product. Now, how do I make sure that your collisions frequency goes up? Well, there's few things that you can do. One thing that you can do to increase the collision frequency is to increase the concentration of your reactants. So maybe if I was using AB here, and if I have only 100 molecules of AB in the beginning, if I increase the amount to maybe 1,000 molecules of AB, I would just generally have more collisions, and in those more collisions, I would have more collisions with proper orientation, and that would make the product. So that's something you want to keep in mind. So increasing the concentrations can generally increase the rate of the reaction. That's the one of the things that I got here. So when you're increasing the concentration here, you would increase the collisions. You would have more collisions, and in those more collisions, you would also have more collisions with proper orientations. And sometimes you can also increase the surface area depending on what type of phases that you're dealing with in the reactants. And this is where, when you increase the concentration, we can generally say that your rate of the reaction is going to increase. And if your rate increases, say generally. But then the question remains that by how much? Like, let's suppose if I double the concentration, will the rate double? Or will the rate triple in that case? Or if I triple the concentration of the reactants, will the rate triples, or maybe the rate changes by some other factor? That's in a question for a separate video. But generally speaking, you want to make sure you know, as you're increasing the concentration, your rate also goes up because of increased amount of collisions. And this is where, like, you start getting the orders of the reactions and stuff like this. The order of the reactions comes from the concentration. Now, the second factor that you can have is the temperature. Now, if you increase the temperature, the kinetic energy goes up. So when the kinetic energy goes up, that means the velocity of the molecule that are going to be moving also goes up. So if they are moving faster, that means they are going to be colliding more often as well. And if they're colliding more often, that means you're increasing the amount of collisions, and that would also increase the amount of collisions with good orientation. Now, not only that, the temperature increase also give enough energy to overcome the activation energy. So it's not really helping one way, but the temperature typically helps two ways. Like, you increase the kinetic energy of the molecules, where you can see more collisions per second or per minute, but then not only that, and an increasing energy will also give you energy to those molecules that they can overcome the energy of activations easily. So typically temperature also increase the rate of the reaction. So as the temperature goes up, the rate also goes up. The third factor that you can kind of go back and look at is the catalyst and the enzyme. Now, what I said earlier that if you go back here, the concentration will only help with the collisions. All right, so more concentration means more collisions, and that eventually means more collisions with proper orientation. Now, the temperature can also help with the collisions because they will be moving faster, so that means they will be frequently colliding with one another. But not only that, the temperature can also make sure that the starting materials have enough energy to overcome this activation energy barrier easily. So the temperature is kind of helping two ways you can think of. The concentration only helps with the collision. Now the activation energy with the catalyst. So what catalyst does, it actually lowers the activation energy. So that means it increases the rate of the reaction. Now, how does that look like? So let me go back and kind of copy this and bring this down. Now, I can say, suppose this was an uncatalyzed reaction that we had originally proposed. Now, as soon as you add in a catalyst to this particular reaction, your pathway may not look the same, but it's gonna look more likely this. So your starting material energy doesn't really change. That's another thing you want to keep in mind. The position of reactants and the position of the products does not change, but what it does, it kind of decreases the amount of high energy that you have to kind of go up in order to convert it to the products. So now you decrease this activation energy that you got here. So I can say this is the EA with catalyst or enzyme. So if you have decreased the amount of catalyst amount of activation energy here, you will possibly have more collisions kind of going over this hump and making the product in this case. So that's how the catalyst or enzymes help to speed up the reaction. So those are the three things that you gotta keep in mind, like how the reaction rate is affected by those three factors and how they are affected in terms of what they are really doing in terms of the collisions and in terms of the activation energy.